Our planet should have been a frozen wasteland for billions of years. Earth today is a vibrant blue marble, teeming with life under a warm sun. But rewind the clock 4 billion years, and the sun was a faint, dim star, shining with only 70% of its current warmth. By every basic calculation, that weak sunlight should have turned our entire world into a lifeless ball of ice. Yet we know for a fact it did not. Ancient rocks tell a story of flowing water and even primitive life. This glaring contradiction is known as the faint young sun paradox, and it is one of the most fascinating detective stories in all of science. By the end of this journey, you will understand the ingenious ways our planet cheated a cosmic deep freeze. We will dig into clues buried in billion-year-old stones, explore wild theories of alien atmospheres, and see how Earth's own geology might have rigged the thermostat. How does a world stay warm when its star provides so little heat? The science behind this paradox begins with understanding our own star's life story. In the early 1970s, astronomers Carl Sagan and George Mullen were piecing together the history of our solar system when they stumbled upon a glaring inconsistency. Their calculations, based on the well-established principles of how stars work, showed that the young sun was fundamentally different from the one we see today. According to stellar evolution models, stars like ours are born from collapsing clouds of gas and dust. The nuclear fusion engine at their core, which converts hydrogen into helium, does not ignite at full strength immediately. Think of it like lighting a campfire. At first, you have a small, flickering flame that struggles to provide warmth. Over many hours, as the logs catch and the bed of coals grows, the fire becomes a steady, roaring source of heat. Our sun followed a similar, albeit vastly slower, path. For billions of years, the process of fusion itself has been gradually changing the sun's interior. As hydrogen is fused into helium, the core becomes denser and hotter, which in turn makes the fusion reactions more vigorous. This causes the star to slowly, inexorably grow brighter over time. The numbers are startling. When life was first taking hold on Earth roughly 4 billion years ago, our sun shone with only about 70% of the brightness it has now. That is a massive deficit of energy. To put it in everyday terms, if you took the sunlight that warms your skin on a pleasant spring day and reduced it by nearly a third, you would be left with the weak, pale light of a late autumn afternoon every single day for eons. This is not a guess or a theory, it is a fundamental prediction of astrophysics, as solid as our understanding of gravity, and it sets the stage for the central mystery. With so little warmth arriving from the heavens, how did Earth's oceans remain liquid instead of freezing solid from pole to pole? The paradox was now officially born, a puzzle written in the cold, hard light of a faint young star. That 70% sunlight deficit is not just a number on a page. It translates to a very real, very cold reality for our young planet. If we take Earth as it is today, with our current atmosphere and continents, and simply dial back the sunshine by 30%, the outcome is brutally simple. Our average global temperature would plummet. Climate models put that number at around -20 degrees Celsius or about -4 degrees Fahrenheit. That is not just a cold winter, that is a permanent planet-wide deep freeze. The entire surface from the equator to the poles would be encased in a thick, unbroken shell of ice. Oceans would become solid, reflecting even more sunlight back into space, locking the world into an eternal, glittering winter. Scientists have a name for this state, a Snowball Earth, and we have strong evidence it actually happened at least twice in our planet's later history. So the logical expectation is that our world should have been born a snowball, trapped in ice for its first 2 billion years under that faint young sun. Yet the rocks tell a completely different story. The oldest sedimentary stones we can find, dating back over 3.8 billion years, show ripple marks and minerals that only form in the presence of liquid water. Even more astonishing, the fossil record holds traces of microbial life from at least 3.5 billion years ago. You do not get thriving colonies of bacteria in a global ice skating rink. So here is the undeniable tension at the heart of the paradox. The astrophysics says freeze, the geology says thaw. Both cannot be true under the rules we thought we understood. Our planet was clearly warm enough for water to flow and life to begin, but the sun was not providing the heat to make that possible. Something else, some powerful planetary secret, must have been at work, bending the rules of climate to keep the young Earth from turning into a permanent ice cube. The most obvious suspect in this planetary warming mystery is right above us. Earth's atmosphere itself holds the key, acting not just as a layer of air, but as a vital temperature regulator. The mechanism is beautifully simple, often called the greenhouse effect. Sunlight, in the form of shortwave radiation, passes easily through our atmospheric gases and warms the ground. The Earth then radiates that heat back outward, but has longer wavelength infrared energy. Certain gases in the air are exceptional at absorbing this outgoing infrared radiation, trapping the heat close to the surface before it can escape into the cold void of space. Think of it like a cozy blanket on a chilly night. The blanket does not create heat, but it slows down its loss, keeping you warm. Our modern atmosphere, with its current mix of gases, provides a blanket that raises our planet's temperature by a life-saving 33 degrees Celsius compared to an airless rock. For the young Earth, the solution seemed straightforward. What if its atmospheric blanket was simply much, much thicker? If the faint sun was providing only 70% of today's warmth, then the ancient atmosphere must have trapped vastly more heat to compensate. This points the finger directly at greenhouse gases with two prime suspects. The first is carbon dioxide, or CO2, a gas we are intimately familiar with today. It is released by volcanoes, and on a young, violently active Earth, volcanic eruptions would have been far more frequent and immense. Imagine a world where the crust was thinner, the mantle hotter, and volcanic plumes constantly spewing gases into the skies. This relentless outgassing could have built up an atmosphere dense with carbon dioxide, perhaps hundreds of times thicker than today's levels, wrapping the planet in a supercharged heat-trapping layer. But carbon dioxide might not have worked alone. The second suspect is methane, or CH4. Methane is an even more potent greenhouse gas molecule, and in an atmosphere without oxygen, which the early Earth lacked, methane could have persisted and accumulated. Its possible sources were everywhere, from the same volcanic activity to the earliest forms of microbial life already beginning to metabolize their surroundings. A thick, hazy atmosphere rich in carbon dioxide and methane could have been the hero our planet needed, bending the rules of physics to keep the oceans liquid under a dim sun. For decades, this super greenhouse theory was the leading and most elegant solution to the paradox. It made perfect sense, fitting neatly with our understanding of planetary infancy. But as with any good detective story, the most obvious suspect soon faced some very hard questions. But a scientific theory, no matter how elegant, needs evidence. It needs proof etched in stone. To test the super greenhouse idea, researchers became geological detectives, searching for clues locked within the oldest rocks on Earth. Their mission was to find a chemical fingerprint, a signal that could reveal exactly what gases filled the ancient air. One of their most valuable pieces of evidence comes from a surprising source: ancient dirt. Paleosols are fossilized soils, the preserved ground surface of a world billions of years old. When rainwater falls through an atmosphere rich in carbon dioxide, it forms a weak acid called carbonic acid. This acidic water then percolates through the soil, reacting with minerals and leaving behind a distinct chemical signature. By meticulously analyzing the ratios of elements in these paleosols, scientists can work backwards to estimate how much carbon dioxide was in the air when that soil formed. It is like finding an old, faded photograph and using forensic techniques to determine the exact lighting conditions when it was taken. Another crucial clue comes from the oceans in the form of banded iron formations. These stunning, striped rocks, layers of red iron oxide and gray silica, were deposited in the deep sea over eons. Their formation is tied directly to the chemistry of seawater, which itself is influenced by the atmosphere. The amount of iron that could remain dissolved and then precipitate out in these beautiful bands depends on factors like ocean acidity, which is controlled by atmospheric carbon dioxide levels. By studying these geological tapes, researchers can get another independent estimate of the ancient air's composition. The detective work goes even deeper to the atomic level through the analysis of isotopes. Different forms of the same element, like carbon, have slightly different weights. Living organisms and certain geological processes prefer one isotope over another. By measuring the ratios of these isotopes in incredibly ancient marine sediments, or even in tiny, nearly indestructible mineral crystals called zircons, scientists can infer the global carbon cycle and, by extension, the likely pressure of carbon dioxide in the atmosphere. The early results from these lines of inquiry seem to support the super greenhouse theory. Some studies of paleosols suggested carbon dioxide levels could have been 100 times higher than today, more than enough to compensate for the faint sun. For a while, the case appeared closed, but science is a process of constant questioning. As more rocks were analyzed and methods refined, complications emerged. The geological record is not a perfect book. It is a tattered, burned, and rewritten manuscript with most of its pages missing. The evidence is often ambiguous, open to multiple interpretations. Some paleosol studies began to yield contradictory numbers, suggesting much lower carbon dioxide levels that simply could not provide the necessary warming on their own. The banded iron formations told a complex story that did not always line up neatly. The paradox, it seemed, was not so easily solved. The very high carbon dioxide estimates were challenged, and a new, unsettling question began to form. What if the greenhouse blanket was never thick enough? Methane offered a tantalizing alternative. While carbon dioxide was a reliable suspect, methane was the wild card, a greenhouse gas with a hidden power. Molecule for molecule, methane can trap over 25 times more heat than carbon dioxide over a century. In the thick, oxygen-free air of the early Earth, this gas could have been a climate supercharger. Picture a world not just under a faint sun, but veiled in a perpetual golden-orange haze. This would not have been a clear sky, but a global photochemical smog. A soupy layer of organic hydrocarbons created as sunlight broke methane molecules apart and reformed them into more complex compounds. This haze itself could have acted as an additional blanket, both absorbing sunlight and trapping heat radiating from below, creating a double-layered insulation effect. Where would all this methane have come from? The most compelling source points directly to life itself. The earliest known organisms were likely methanogens, microbes that thrive in environments devoid of oxygen, like deep sea vents or muddy sediments. They consume simple chemicals like hydrogen and carbon dioxide and exhale methane as a waste product. This creates a profound link. The very life struggling to begin on a cold world might have been its own salvation, unconsciously firing up the planetary furnace through its own metabolism. The faint young sun paradox and the origin of life story become intertwined, a beautiful feedback loop where biology helps create the conditions necessary for its own survival. Yet methane is a fickle ally. Its very strength is also its weakness. Unlike carbon dioxide, which can persist in the atmosphere for centuries, methane is chemically fragile. It breaks apart easily under ultraviolet sunlight, and without a protective ozone layer, that destructive UV light would have been intense. This means any methane blanket would have been leaky, requiring a constant, massive supply from volcanoes or microbes just to maintain its warming power. Furthermore, the complex atmospheric chemistry it triggers is a nightmare to model. As methane breaks down, it sets off a cascade of reactions that can produce other greenhouse gases, but also can generate hydrogen gas, which is light enough to escape Earth's gravity entirely, slowly bleeding the planet of its atmospheric mass over billions of years. The photochemical haze that helps trap heat also reflects incoming sunlight back to space, which could cool the planet. Getting the balance right in a computer simulation is extraordinarily difficult, a delicate dance between warming and cooling effects that depends on precise, unknown quantities. So while a methane-rich atmosphere remains a compelling and elegant piece of the puzzle, it is difficult to prove it was the sole or even the primary hero. The geological evidence for such an atmosphere is even more elusive than for carbon dioxide, leaving it as a brilliant but unproven hypothesis. If both leading greenhouse suspects face serious questions, then the investigation must widen. We have to look beyond the air itself to the very ground beneath our feet and the color of the young planet from space. But the atmosphere's story is not just about what it was made of, but how much of it there was. Beyond the specific greenhouse gases lies a more fundamental physical property: sheer weight. The total mass of the air pressing down on the ancient surface might have been the hidden variable that tipped the scales. Think of our modern atmosphere as a light comforter. The super greenhouse theory proposed adding an electric heating pad to that comforter, but another idea suggests the blanket itself was once a massive, heavy duvet. This theory focuses on pressure, and its most likely source was a gas we often overlook: nitrogen. Molecular nitrogen, or N2, makes up about 78% of our air today, but it is largely a bystander in the greenhouse effect. It is transparent to both incoming sunlight and outgoing infrared radiation. However, its role changes dramatically if there is simply more of it. A much denser atmosphere, bulked up by a vast reservoir of nitrogen, would have had a profound physical impact through a process called pressure broadening. Here is how it works. Individual gas molecules in the air absorb specific wavelengths of infrared light, like tiny tuning forks that only vibrate to certain notes. In a thin atmosphere, these absorption lines are narrow and precise. But when you pack more molecules into the same space, increasing the pressure, those molecules collide with each other more frequently. These collisions slightly blur or broaden their tuning, allowing each molecule to absorb a wider range of infrared wavelengths. It is like turning a single, pure musical note into a rich, resonant chord. For greenhouse gases like carbon dioxide and methane, this pressure broadening supercharges their natural ability. They become vastly more efficient at capturing the heat trying to escape from the planet's surface. A thicker nitrogen background, therefore, would have acted as a universal amplifier, making every greenhouse gas molecule more potent without needing to change its concentration. The faint young sun's warmth would have been trapped with far greater efficiency under this heavy, pressurized sky. The question becomes, is there any evidence that Earth's air was once so much denser? Researchers have looked for clues in some of the most delicate fossils imaginable. Tiny gas bubbles trapped in ancient amber, the fossilized resin of trees, can preserve samples of the atmosphere from tens of millions of years ago. While this does not reach back to the planet's earliest days, it suggests atmospheric pressure has fluctuated significantly over deep time. More direct and more ancient evidence might come from the fossilized impressions of raindrops. When a raindrop falls onto fine volcanic ash or soft sediment, it leaves a tiny crater. The size and shape of that crater depends on the size of the raindrop and the speed at which it was falling. And a raindrop's terminal velocity is controlled by the density of the air it is falling through. In a thicker atmosphere, air resistance is greater, so raindrops fall more slowly and strike the ground with less force. By studying the imprints of fossil raindrops from over 2 billion years ago and comparing them to models, some scientists have argued the ancient air could have been nearly twice as dense as it is today. This paints a vivid picture of a young world under a heavy, pressurized sky where clouds might have hung lower, winds felt thicker, and the very sound of thunder would have been a deeper, more muffled boom. The nitrogen factor adds a crucial layer of complexity, moving the mystery beyond a simple search for magical greenhouse gases and into the realm of the atmosphere's raw physical power. All these atmospheric theories share one critical assumption: that Earth was a passive recipient of its climate, at the mercy of whatever gases filled its skies. But our planet is not a passive rock. It is a living, breathing engine of geology, and it possesses a built-in thermostat of astonishing elegance, a system that has maintained a stable climate for billions of years. This is the carbon silicate cycle, and it is the master regulator that may have solved the paradox from the ground up. To understand it, we need to follow a single carbon atom on an epic journey. It begins deep within the Earth, where immense heat and pressure melt rock. Trapped within this molten magma is carbon dioxide. When a volcano erupts, it releases this CO2 into the atmosphere, where it acts as a greenhouse gas, warming the planet. This is the heating phase, but here is where the genius of the system kicks in. That warmth is not an end point, it is a trigger. A warmer world means more evaporation from the oceans and more rainfall. Rainwater, slightly acidic from absorbing atmospheric CO2, falls onto the continents and reacts with silicate rocks in a process called chemical weathering. Think of it like a planetary antacid tablet. The acidic rain slowly dissolves the rock, and in the chemical reaction, the carbon dioxide from the air is pulled out and transformed. It gets washed into the oceans as dissolved bicarbonate. There, tiny marine organisms use it to build their shells and skeletons. When these creatures die, their shells sink to the seafloor, accumulating over millennia into thick layers of limestone and other carbonate rocks. The carbon is now locked away in stone, and the atmosphere cools slightly as its greenhouse blanket thins. This is the cooling phase, but the journey is not over. The relentless motion of Earth's tectonic plates comes into play. The seafloor, with its layers of carbonate sediment, is slowly dragged back into the planet's interior at subduction zones. There, the intense heat and pressure cook the rocks, releasing the carbon dioxide back into the magma, ready to be vented once again by a future volcano. And so the cycle begins anew. This is a perfect negative feedback loop. If the planet gets too warm, weathering accelerates, pulling more CO2 from the air, which cools things down. If it gets too cold, weathering slows, allowing volcanic CO2 to build up and warm the planet. It is a self-correcting system, a planetary thermostat with a reaction time of hundreds of thousands of years. For the early Earth, this cycle was almost certainly operating, but the dial was cranked to its maximum setting. The planet was far more geologically hyperactive. The crust was thinner, the mantle hotter, and seafloor spreading was dramatically faster. This meant more frequent and more violent volcanic eruptions, injecting colossal amounts of CO2 into the atmosphere at a staggering rate. The thermostat was set to broil, maintaining those sky-high carbon dioxide levels needed to compensate for the faint sun. The weathering side of the equation would have been intense as well, with higher temperatures driving fierce rainstorms across the first barren continents. But the volcanic supply was simply so overwhelming that it kept the atmospheric CO2 concentration persistently high. The carbon silicate cycle did not just warm the young Earth, it stabilized it, preventing wild swings between inferno and icebox long enough for life to gain a fragile foothold. This geological heartbeat provided the consistent, if alien, warmth that the faint young sun could not. Yet the atmosphere is more than just a chemical mix or a physical weight. It is a dynamic canvas painted with clouds, and this introduces one of the most unpredictable variables in the entire climate equation: clouds are the wild cards of planetary temperature, a double-edged sword with the power to either warm or cool the world depending on their type, altitude, and coverage. This delicate balance is measured by a planet's albedo, its overall reflectivity. A bright, shiny surface like fresh snow reflects most sunlight back into space, cooling the planet. A dark surface like the deep ocean or a forest absorbs that light as heat. For the young Earth, cloud cover could have tipped the scales of the faint young sun paradox in a surprising way. Imagine the early planet, its vast global ocean broken only by scattered, barren volcanic islands. The sky above that water might have looked profoundly different from our own. Today, clouds often form around tiny particles lofted into the air, things like dust, pollution, or pollen. These are cloud condensation nuclei, the seeds around which water vapor can gather and form droplets. But on that primordial world, with far less continental dust and no life to emit organic particles, the air may have been remarkably clean. Fewer seeds could have meant fewer clouds overall, or clouds made of larger, fewer water droplets. And the size and number of droplets in a cloud dramatically changes its reflectivity. A cloud with many small droplets presents a brighter, whiter surface, bouncing more sunlight away. A cloud with fewer, larger droplets is darker and more transparent, allowing more solar energy to pass through to warm the ocean below. So, a lower, patchier cloud deck over the ancient seas might have meant a darker planet, one that absorbed more of the faint sun's precious light instead of reflecting it uselessly into space. But the story of clouds gets even more complex. Not all clouds cool the Earth. High, wispy cirrus clouds made of ice crystals are notoriously poor at reflecting incoming sunlight. Instead, they act like a transparent greenhouse barrier, letting solar energy in but trapping the heat radiating back from the surface. If the ancient atmosphere favored the formation of these thin, heat-trapping cirrus clouds over thicker, reflective ones, the net effect could have been a significant warming boost. The planet's albedo would have been lower, its overall color from space a deeper, heat-absorbing blue rather than a brilliant, reflective white. This subtle shift in cloud physics could have provided just enough extra warmth to keep the global thermostat above freezing. Scientists today admit that clouds represent one of the greatest uncertainties in modeling not just Earth's past, but its future climate. For the Hadean and Archean eons, the variables are immense and the evidence is indirect. We are left with a fascinating conundrum. Did a cleaner atmosphere with fewer clouds let the young Earth drink in more sunlight? Or did a different atmospheric chemistry brew up a persistent cirrus blanket that held heat close? This uncertainty makes clouds a central frontier in the search for a complete answer, a reminder that sometimes the most familiar features in our sky hold the deepest mysteries. But what if the paradox begins with a flawed assumption? We have taken the faintness of the young sun as an unshakable fact, a cornerstone of astrophysics. Yet science is built on questioning even its most solid foundations. Could our models of stellar evolution, while overwhelmingly successful, be missing a crucial detail about our own star's fiery youth? The idea is not to discard the theory, but to refine it. Perhaps the young sun was not just a dimmer version of its current self, but a fundamentally more active and violent child. One compelling line of inquiry focuses on rotation. Stars are born spinning rapidly, and they gradually slow down over billions of years as their magnetic fields interact with the stellar wind, a process like a spinning ice skater extending their arms. A faster rotation in a young star drives a much more powerful magnetic dynamo. This means the infant sun might have been laced with intense magnetic fields, spawning colossal sunspots and unleashing torrents of high-energy radiation. Its surface could have been a continuous storm of ultraviolet and X-ray flares, hundreds or even thousands of times more powerful than anything we see today. This changes the energy equation in a subtle but profound way. While the total visible sunlight, the warmth we feel, was indeed lower, the flood of high-energy particles and radiation could have had a dramatic indirect effect on Earth's atmosphere. When these intense ultraviolet rays slam into the upper atmosphere, they don't just heat it, they rip molecules apart in a process called photodissociation. This can break apart water vapor high up, for example, allowing lightweight hydrogen to escape and altering the chemistry of the entire atmospheric envelope. More importantly, this constant bombardment could have prevented the buildup of certain cooling gases or even helped manufacture alternative greenhouse gases through complex chemical reactions. It is a different kind of warmth, not a gentle blanket but a series of explosive sparks that keep the engine running. Another, more radical suggestion is that the young sun was slightly more massive. Even a few % more mass in its early life would mean a hotter, brighter core and a stronger gravitational pull, compensating for some of the predicted faintness. As it aged, the relentless solar wind, stronger in its youth, could have stripped away that extra mass over eons, leaving us with the sun we measure today. While evidence for this is less certain, it highlights the beautiful complexity of the puzzle. The faint young sun paradox may not be a simple error in our stellar models, but a sign that we need to paint a more nuanced portrait of stellar adolescence. The sun's early fury, its violent ultraviolet tantrums, might have provided just enough of a nudge to the planet's climate system, working in concert with a thick atmosphere and a powerful geological thermostat to defy the ice. The solution, it seems, was never going to be one single thing, but a chorus of strange and ancient mechanisms singing together against the cosmic cold. Earth's story of defying the ice is not unique in our solar system. To truly appreciate the scale of this cosmic puzzle, we must look beyond our own world to the silent histories written on the faces of our neighboring planets. The faint young sun shone on them all, and their fates reveal just how delicate the balance of climate really is. Take Mars, the red planet that today is a frozen, dusty desert with an atmosphere thinner than a wisp. Yet, orbiting cameras have sent back breathtaking images of dried-up river valleys, vast floodplains, and even the ghostly outlines of ancient lakebeds and deltas. These are not the scars of a sudden catastrophe, but the patient etchings of liquid water flowing and pooling over thousands or even millions of years. This presents us with a mirror of Earth's own paradox. Mars is farther from the sun than Earth, receiving even less of that already faint sunlight. For water to flow freely there, its early climate must have been radically different. The planet needed a much thicker atmosphere, rich in greenhouse gases, to trap enough heat to prevent that water from instantly freezing or evaporating. The evidence suggests Mars once had exactly that, a cozy atmospheric blanket that kept its surface warm and wet, possibly for a long stretch of its history. So what happened? The tragedy of Mars lies in its size. It is a smaller world with less gravity to hold onto its atmosphere. As the planet's internal heat faded, its volcanic activity slowed, shutting down the main source of replenishing gases. The solar wind, that stream of charged particles from the sun, then began to strip the Martian air away molecule by molecule, a process that continues to this day. Without a robust carbon silicate cycle or the geological engine to sustain it, the greenhouse collapsed, the planet grew cold, the water froze or vanished into space, and the atmosphere became the tenuous ghost we see now. Mars solved the faint young sun paradox, but only temporarily, before losing the very elements that made its brief spring possible. Now look in the other direction, toward Venus. If Mars is a cautionary tale of a greenhouse lost, Venus is the nightmare of a greenhouse gone berserk. Today, it is a hellscape with a surface hot enough to melt lead and an atmosphere of crushing carbon dioxide pressure. But in the distant past, under that same faint sun, Venus may have been very different. Some models suggest it could have even had liquid water oceans for a time. Being closer to the sun, it received more of that precious early warmth. The problem for Venus was one of location and feedback. being warmer, any water on its surface would have evaporated more readily, filling the atmosphere with water vapor, a powerful greenhouse gas. This would have warmed the planet further, evaporating more water in a vicious cycle known as a runaway greenhouse. At a certain point, the heat became so intense that all the water in the oceans was driven into the upper atmosphere. There, ultraviolet light from the sun broke the water molecules apart, allowing the lightweight hydrogen to escape into space forever. The oxygen was left behind to react with rocks or get locked into other compounds. What remained was a massive, suffocating atmosphere of carbon dioxide with no water left to drive a weathering cycle to draw it down. The planet's thermostat broke, stuck permanently on maximum heat. Venus, it seems, solved the paradox too well, cooking itself into a permanent fever. This comparative view of our planetary neighborhood is what scientists call comparative planetology, and it turns the faint young sun paradox from an Earth mystery into a solar system principle. It shows us that the paradox was a universal challenge for rocky worlds in our sun's early days. The ultimate climate fate of each planet was not written by the sun alone, but by a combination of factors, a cosmic roll of the dice. Distance from the star set the starting line. Planetary size and gravity determined whether it could hold onto its atmospheric blanket, and the presence of an active tectonic geology decided if that planet had a working thermostat, a way to regulate the heat and maintain balance over billions of years. Earth, it turns out, won the solar system lottery. It was at the right distance, was large enough to retain its atmosphere and oceans, and was blessed with that relentless geological heartbeat, the carbon silicate cycle, which provided stability. Our story is not isolated, but one chapter in a grander narrative of three worlds born under the same faint star, each following a dramatically different path toward fire, ice, or enduring life. This planetary drama of fire and ice finally introduces its most unlikely protagonist, life itself. For billions of years, the story of Earth's climate was not just written by volcanoes and sunlight, but by the silent, relentless work of microscopic organisms. The first life forms were not mere passengers on a planet struggling to stay warm. They became active engineers of their own environment, participating in a delicate balancing act that may have been crucial to solving the paradox. The earliest ecosystems were likely vast, slimy mats of microbes coating the shallow seafloors and coastlines. Within these microbial cities, different species performed chemical transformations that directly manipulated the atmosphere. Some, the methanogens we met earlier, consumed simple compounds and exhaled methane, adding to the greenhouse blanket. Others, the ancestors of cyanobacteria, began to perfect a revolutionary new technology, photosynthesis. They learned to use sunlight to power their cells, but their early version had a side effect. It did not produce oxygen. Instead, it likely consumed carbon dioxide and produced other gases, subtly shifting the atmospheric mix. This microbial world created a kind of biological thermostat, a crude but effective feedback loop where life's waste products influenced the climate, and the climate in turn shaped which life could thrive. It is a less rigid version of an idea known as the Gaia hypothesis, where the biosphere and the physical planet are seen as a single, self-regulating system. For the young Earth, these microbial mats were that system's first tentative control knobs, turning the dials on methane and carbon dioxide in response to the faint sun's whims. The most dramatic proof of life's power to reshape a planet arrived with a microbial revolution, the moment cyanobacteria evolved oxygenic photosynthesis. This was a game-changer on a cosmic scale. These tiny organisms figured out how to use sunlight to split water molecules, harnessing the hydrogen for energy and releasing pure, gaseous oxygen as a waste product. For them, it was simply a better way to eat. For the planet, it was a slow-motion poison gas attack. Oxygen was a deadly toxin to most of the ancient biosphere, rusting metals and breaking apart organic molecules. It also spelled doom for the methane greenhouse. Oxygen reacts violently with methane, breaking it down into carbon dioxide and water. Carbon dioxide is a weaker greenhouse gas, so as cyanobacteria proliferated in the oceans, pumping out oxygen, they began to dismantle the very atmospheric blanket that had kept the world warm. This set the stage for one of the greatest climate catastrophes in Earth's history, the Great Oxidation Event, around 2.4 billion years ago. The rise of oxygen likely triggered a monumental cooling. As the methane shield was chemically scrubbed from the air, the planet's ability to trap the sun's faint heat plummeted. Many scientists believe this directly caused the first global glaciation, a Snowball Earth event where ice sheets may have reached all the way to the equator. In a profound irony, life, in its struggle to survive and innovate, accidentally triggered a planetary deep freeze, nearly extinguishing itself in the process. The biological thermostat had swung wildly out of balance, demonstrating that life's influence was powerful, but not always gentle or wise. Yet even this disaster reveals the resilience of Earth's interconnected systems. The Great Freeze itself may have been part of a longer-term correction. As the ice covered the continents, the chemical weathering of rocks, which consumes carbon dioxide, would have ground to a halt. But volcanoes kept erupting under the ice, steadily pumping carbon dioxide into the atmosphere with no way for the planet to draw it down. For millions of years, this volcanic carbon dioxide built up to staggering levels, perhaps thousands of times higher than today. Eventually, this supercharged greenhouse effect grew strong enough to melt the global ice, releasing the planet from its frozen prison in a rapid and violent thaw. The aftermath was a world reset, with a new atmosphere rich in oxygen and carbon dioxide, setting the stage for entirely new forms of life to evolve. This epic cycle shows life as a central, if unpredictable, character in the climate drama. It was not a separate entity from the rocks and the air, but woven into the same fabric. The faint young sun paradox, therefore, finds its most elegant solution not in a single mechanism, but in a symphony of geology, astronomy, and biology. Our planet stayed warm because it was alive in every sense, from its molten core to its microbial seas, all working in a complex, self-regulating dance under the light of a faint young star. There is one more atmospheric recipe, far stranger than any we have considered. What if the air our planet first breathed was not nitrogen or carbon dioxide, but the lightest element in the universe? This is the hydrogen hypothesis, a radical reimagining of Earth's infancy. For a brief window, perhaps just a few 100 million years after its formation, our world may have been swaddled in a vast, puffy envelope of primordial hydrogen. This gas, left over from the solar nebula that birthed the planets, would have been gravitationally captured by the young, massive Earth. Hydrogen itself is only a weak greenhouse gas when alone, but its true power lies in its behavior. Being so incredibly light, it does not cling close to the surface like our modern air. Instead, it billows outward, creating an extended atmosphere that reaches far into space, thousands of kilometers high rather than just 100. This changes the physics of warming in two clever ways. First, that expansive atmospheric halo is exposed to the young sun's intense barrage of ultraviolet radiation. The UV light heats the upper layers of this hydrogen shroud directly, and that heat then trickles down toward the surface. Second, and more importantly, is a process called collision-induced absorption. When hydrogen molecules bump into heavier companions like water vapor or even other hydrogen molecules under high pressure, they temporarily form brief, loose complexes. These collisions momentarily change the molecule's electrical properties, allowing them to absorb a much wider range of infrared heat radiating from the planet below. It is a greenhouse effect powered not by a gas's innate ability, but by the sheer chaos of constant collisions in a thick, extended sky. A hydrogen-dominated atmosphere could therefore have been a surprisingly effective blanket, one uniquely suited to a time when the sun was dim in visible light but furious in ultraviolet. The warmth it provided might have been just enough to keep the first oceans liquid, but such an atmosphere was always on borrowed time. Hydrogen is so light that the gentle push of the solar wind and the energy of sunlight can give individual molecules enough of a kick to reach escape velocity. Over millions of years, this precious primordial blanket would have slowly bled away into the void, stripped by the very star it was helping to defy. The evidence for this fleeting hydrogen era is incredibly difficult to find, as it left almost no chemical trace in rocks that formed after it vanished. Yet, the hypothesis remains compelling because it fits a pattern we see elsewhere. The largest moons in our solar system, like Saturn's Titan, hold onto thick atmospheres precisely because they are rich in nitrogen and methane, which are heavier and less likely to escape. Earth's journey from a hydrogen-wrapped infant to the nitrogen-oxygen world we know may have been a necessary atmospheric metamorphosis. This idea pushes the boundaries of conventional thinking, reminding us that the solutions to the faint young sun paradox might be as varied and creative as the scientists who dream them up. The sun was not the only source of warmth for the young Earth. Our planet's own inner fire burned far more fiercely in its youth, and this internal heat may have played a subtle but vital role in the Great Thaw. To find this hidden furnace, we must look not just to the core but to the sky at our closest celestial companion. 4 billion years ago, the Moon was much closer to Earth, perhaps only a fraction of its current distance. This proximity meant its gravitational pull was immensely stronger, and it would have dominated the sky as a colossal, looming presence. The tides it generated were not the gentle, rhythmic swells we see today. They were planetary-scale tsunamis, walls of water hundreds of meters high that would have swept across the globe every few hours, relentlessly grinding the continents and churning the oceans into a frothing chaos. This constant, violent flexing did more than just move water. It worked on the very rock of the planet itself. As Earth's shape was distorted by the Moon's fierce gravity, friction was generated deep within its mantle. This process, called tidal heating, is like repeatedly bending a metal coat hanger back and forth until it becomes hot to the touch. On a planetary scale, that friction translates into a massive influx of geothermal energy. We see this effect in action today on a moon of Jupiter, Io, where the gravitational tug of war between Jupiter and its other satellites squeezes and stretches Io so violently that it becomes the most volcanically active world in the solar system, its surface constantly remade by erupting lava. While Earth was never that extreme, a closer moon would have supercharged its internal engine. This tidal heating would have supplemented the planet's natural geothermal warmth, potentially raising the temperature of the ocean floor and creating vast networks of hydrothermal vents. These vents could have acted as localized oases, pumping heat and minerals into the deep sea, creating warm pockets in an otherwise chilly global ocean. This internal warmth had another source, one buried in the very rocks of the young crust. Early in Earth's history, the planet contained a richer abundance of radioactive elements like uranium, thorium, and potassium. These elements decay over time, releasing heat as a byproduct. Billions of years ago, there was simply more of this radioactive fuel present, and its decay contributed a significantly higher background warmth to the planet's interior. This heat steadily conducted upward, warming the bedrock beneath the oceans and continents. Now it is crucial to understand the scale. Even combined, this enhanced geothermal and tidal heat flux was tiny compared to the energy arriving from the sun. It could not have warmed the entire atmosphere or prevented a global freeze on its own. But climate is not always about global averages, it is about niches and refuges. In a world perched on the edge of freezing, this internal warmth could have been the difference between a solid ice shell and a slushy, partially liquid ocean. Under a thin layer of sea ice or in deep, protected basins, the heat rising from below could have maintained pockets of liquid water. These would have been dark, warm havens, shielded from the faint sun but sustained by the planet's own heartbeat. For the earliest life forms, which many scientists believe originated around deep-sea hydrothermal vents, these geothermal oases would have been not just a sanctuary but a cradle. The faint young sun paradox, therefore, might find a partial answer not in the sky above, but in the restless heat below, a reminder that a planet's climate is shaped as much by its own inner dynamics as by the light of its star. Even the planet's own inner fire, however, pales in comparison to the raw, celestial violence that once rained from the sky. There was a time when the solar system itself was a shooting gallery and Earth was the primary target. This period, known as the Late Heavy Bombardment, was a chaotic chapter roughly 4 billion years ago when countless asteroids and comets, remnants of planetary formation, were flung inward, hammering the inner worlds. For hundreds of millions of years, our planet endured a relentless pummeling from space. Each impact was an event of apocalyptic scale, but within that destruction may have lain a brutal, temporary answer to the cold. Think of it not as a gentle warming, but as a series of cosmic defibrillator shocks, jolting the climate system back from the brink of permanent ice. A single large impactor, dozens of kilometers across, would have delivered energy beyond all human comprehension. The moment of collision would have released more power than every nuclear weapon on Earth combined in a fraction of a second. The target rock and a portion of the Earth's crust would not just melt, they would instantly vaporize, blasted into the upper atmosphere as a superheated plume of incandescent gas and dust. If the impact struck an ocean, which was likely given the young planet's surface, vast volumes of seawater would flash into steam. The sky itself would boil. This is where the paradox meets the cataclysm. That vaporized rock and ejected seawater were not inert. They were loaded with climate-altering potential. The vaporized rock released immense quantities of carbon dioxide and sulfur dioxide, powerful greenhouse gases, directly into the stratosphere. Comets, which are essentially dirty snowballs of ice and rock, would have delivered their own payloads of water, carbon dioxide, ammonia, and methane upon impact. In the immediate aftermath, the dust and soot might have blocked sunlight, causing a brief impact winter. But that would soon give way to a far longer and more profound effect, a super greenhouse. The colossal injection of greenhouse gases would have trapped heat with ferocious efficiency. For decades, perhaps even centuries after a major strike, the planet would have entered a state of intense global warming. Temperatures could have soared, melting any nascent ice sheets and keeping the oceans liquid even under the faint sun. The climate would have been thrust into a temporary fever, a planetary sauna maintained by the atmospheric chaos of the impact. This was not a stable, finely tuned solution like the carbon silicate cycle. It was a blunt, traumatic instrument, but stability may not have been what the young Earth needed. It needed repeated interventions, a series of violent resets that prevented the system from settling into a permanent, frozen equilibrium. If the bombardment was frequent enough, with major impacts occurring every few million or even 100,000 years, the planet might have oscillated between periods of cold and episodes of artificial, impact-driven heat. Life, if it had already sparked into existence in deep-sea vents or warm ponds, would have faced near annihilation with each catastrophe. Yet, in the long, quiet intervals between the thunderbolts from space, in those warmed and chemically enriched oceans, it could have persisted, adapted, and slowly spread. The paradox of a faint young sun and a warm Earth might therefore include a chapter written in fire and brimstone from the heavens, a reminder that sometimes the very forces that threaten to sterilize a world can also, paradoxically, keep it alive. Our planet's dance through space is far from a perfect circle. The subtle rhythms of its orbit and spin may have been another crucial piece of the ancient climate puzzle. We know today that long-term climate shifts are influenced by slight variations in Earth's journey around the Sun, called Milankovitch cycles. These cycles involve changes in the planet's axial tilt, the shape of its orbit, and a slow wobble in its rotational axis. Over hundreds of thousands of years, they nudge the distribution of solar energy, contributing to the coming and going of ice ages. Now, cast these cycles back to a time when the sun itself was dim. What if the young Earth's astronomical settings were different? If its axial tilt was more pronounced, for instance, the seasons would have been dramatically more extreme. A greater tilt means more direct, concentrated sunlight at the poles during their respective summers and deeper, darker winters. Under a faint sun, this could have been a vital mechanism. While the winters would have been brutally cold, the intense summer sunlight at high latitudes might have been enough to melt back seasonal ice, preventing it from accumulating into a permanent, planet-spanning sheet. It would have created a pulse of warmth, a yearly thaw in key regions that kept the global climate system from locking up. The shape of Earth's orbit matters just as much. Today, our orbit is nearly circular, but it slowly oscillates between more circular and more elliptical over time. An elliptical orbit means the planet's distance from the Sun changes throughout the year. If the young Earth's orbit was more exaggerated, its year would have featured a pronounced close approach to the Sun, a time when the faint star would have appeared slightly brighter and larger in the sky. This annual pulse of increased solar energy, though temporary, could have delivered a critical dose of warmth during a key season, perhaps enough to break the back of forming ice. It is a concept of concentrated energy, a focusing of that weak sunlight into a more powerful periodic beam. Furthermore, consider the speed of the planet's spin. A faster rotation in its youth before the Moon's gravity gradually slowed it would have fundamentally altered atmospheric circulation. The Coriolis effect, which dictates wind patterns and ocean currents, would have been stronger. This could have driven more efficient heat transport from the equator toward the poles, preventing the high latitudes from becoming cold traps where ice could nucleate and spread. Stronger, more numerous hurricanes might have churned the oceans, mixing warm surface waters with the depths and distributing that precious geothermal heat from the seafloor more widely. These astronomical factors are master redistributors, not creators of heat. They do not add a single watt of energy to the system that the faint sun failed to provide. But on a world balanced on a knife's edge, redistribution can be everything. By concentrating the meager sunlight in time and space, through extreme seasons and elliptical orbits close pass or more vigorous atmospheric mixing, these cycles could have maintained vital ice-free refuges. Picture a slushy, partly frozen world, not a solid snowball. In the tropical latitudes, under a more direct if weaker sun, open water could have persisted year-round. These equatorial oases, kept liquid by the astronomical choreography, would have been crucibles for early life and engines for climate. Open water absorbs sunlight while ice reflects it. So once these corridors of liquid ocean were maintained, they helped the planet absorb more of the precious little energy it received, creating a positive feedback that staved off total glaciation. The solution to the faint young sun paradox, therefore, may not reside in any one place, not just in the air, the rocks, or the heavens, but in their magnificent, synchronized interplay. The geography of our planet's youth was a masterpiece of simplicity, a stark contrast to the complex continents we know today. For hundreds of millions of years, Earth was not a world of green forests and brown mountains, but a single, uninterrupted blue marble. The first continents were nothing more than scattered, barren volcanic archipelagos poking above a truly global ocean. This was a water world, and this fundamental fact may have been its greatest defense against the cold. The absence of vast landmasses changed the rules of climate in profound ways, starting with a simple principle of color. Dark surfaces absorb heat, light surfaces reflect it. The deep blue of an open ocean is one of the darkest natural surfaces on the planet, with a very low albedo, meaning it soaks up sunlight like a sponge. The barren, gray-black rock of those first volcanic islands was not much brighter. Compare this to a modern Earth where brilliant white ice caps, sandy deserts, and green forests covered in snow for part of the year reflect a significant portion of sunlight back into space. The young planet, dressed almost entirely in dark ocean, was perfectly tailored to capture every possible photon of that faint young sun's precious light. It was not a reflective, shiny ball, but a dark, heat-absorbing sphere. Beyond simply absorbing heat, the global ocean possessed a superpower called thermal inertia. Water has an immense capacity to store heat, a property you experience every time you visit a beach in summer. The sand burns your feet by midday, but the ocean remains cool and refreshing. By evening, the sand is cold, but the water retains its gentle warmth. The ocean resists rapid temperature change. On a planetary scale, this global sea acted as a colossal thermal battery. It slowly absorbed the weak solar energy over the long, quiet eons, banking that warmth in its depths. When seasonal shifts or atmospheric changes might have threatened a cooling spell, this vast reservoir of stored heat would have been released, buffering the climate against sudden plunges into ice. It smoothed out the extremes, preventing the wild temperature swings that could have allowed ice to gain a permanent foothold. The climate of the water world was inherently more stable, more resistant to the shock of a faint sun, simply because it had an ocean-sized cushion. This global ocean was also a dynamic engine of heat distribution. Today, our continents act as massive walls, blocking and redirecting the great ocean currents. The Americas form an almost unbroken barrier from pole to pole, forcing currents like the Gulf Stream to turn and weave. The early Earth had no such obstacles. Ocean currents could flow unimpeded around the entire planet, a continuous, planet-girdling conveyor belt. Warm water from the sun-drenched equatorial regions could circulate freely toward the poles, delivering life-giving warmth to high latitudes that might otherwise have frozen solid. Conversely, cooler polar waters could flow back toward the tropics, moderating extreme heat. This unimpeded circulation created a more uniform global temperature, a far cry from the stark contrasts we see today between tropical, temperate, and polar zones. Without continents to get in the way, the planet's circulatory system was at its most efficient, ensuring no part of the world was left in permanent, cold isolation. So we must reimagine the young Earth not as a colder version of our own, but as a profoundly different planetary body, a dark, global ocean drank in the faint sunlight. That ocean's incredible heat capacity stored that energy for millennia, acting as a stabilizing thermal mass, and its unrestricted currents tirelessly distributed that stored warmth from equator to pole and back again. This was not a fragile world teetering on the edge of an ice age, but a resilient, fluid system designed to resist freezing. The water world itself was a foundational solution, the stable platform upon which all the other mechanisms, the thick atmosphere, the geological thermostat, the faintly furious sun, could do their work. The missing continents were not an absence, but the key to a global climate that could endure the long winter of a star's youth. All these ancient mechanisms are now put to the test in the digital crucible of the modern age. Today, scientists don't just speculate about the faint young sun. They build entire virtual Earths inside supercomputers. These are not simple calculators, but staggeringly complex programs known as General Circulation Models, or GCMS. They are the closest thing we have to a time machine for climate. These models divide the planet's atmosphere, oceans, and land into a three-dimensional grid of millions of cells. Into this digital framework, researchers can pour every ingredient of our ancient climate mystery. They dial the solar constant down to 70%. They pump the virtual air full of carbon dioxide, hundreds or even thousands of times today's levels. They layer in a golden haze of photochemical smog from methane. They adjust the atmospheric pressure, making the sky feel twice as heavy. They paint the planet a darker blue, lowering its reflectivity to mimic a water world with fewer different clouds. Then, with a press of a button, they set this digital Earth spinning under its faint star and wait to see if it freezes. The goal is not to find one magic bullet, but to discover which cocktail of conditions keeps the global temperature consistently above freezing for millions of years. The simulations are brutally honest. They reveal dead ends and contradictions. An atmosphere with only slightly elevated carbon dioxide still freezes solid. A thick methane haze alone can warm the planet, but the accompanying photochemical products often cool it too much, or the gas breaks down too quickly. A denser nitrogen atmosphere helps, but it is not enough by itself. The magic, according to the most robust modern models, happens in the combination. The emerging consensus points to a layered solution, a baseline of significantly higher carbon dioxide, perhaps 10 to 100 times modern levels, provided by a hyperactive carbon silicate cycle, forms the foundation. This is amplified by a moderately denser atmosphere, where pressure broadening supercharges the greenhouse effect of every CO2 molecule. On top of this, a lower planetary albedo from darker oceans and a cloud deck that favored heat trapping over sunlight reflection lets in every possible photon of that faint sunshine. The models suggest these factors working in concert could have maintained a global average temperature near or even above the freezing point of water. It is a symphony, not a solo. The faint young sun paradox was not solved by a lone hero, but by a planetary alliance of geology, atmospheric physics, and celestial circumstance. The supercomputer simulations show us that our world's early warmth was a precarious, hard-won balance, a testament to the intricate and interconnected systems that have always governed this pale blue dot. Yet this planetary balancing act was not always perfect. There were moments long after the faint young sun era when the delicate system failed catastrophically. The geological record reveals at least 2, and possibly more, periods where our planet did not just grow cold, but transformed into a glittering, lifeless marble of ice from pole to equator. These are the Snowball Earth events, and they represent a stunning reversal of the paradox. After billions of years of defying the freeze, Earth plunged headlong into it, not because the sun grew dimmer, but because its own internal climate controls were violently disrupted. The most profound of these global glaciations occurred during the Proterozoic Eon, roughly 700 million years ago. Imagine a world where the ice did not stop at the polar circles, but marched relentlessly onward, swallowing continents and freezing oceans solid until even the equator was buried under a kilometer-thick sheet of white. The tropical seas, once warm oases, became a solid plain of ice under a pale, weak sun. This was not a seasonal winter, it was a planetary deep freeze lasting for millions of years. The evidence for this incredible scenario is written in stone. Geologists find glacial deposits, the rubble pushed along by ancient ice sheets on every continent and in locations that were squarely at the equator at that time. You do not get tropical glaciers unless the entire planet is cold. Mixed in with these icy sediments are distinct layers of iron-rich rock, banded iron formations, which had largely disappeared from the record for over 1 billion years. Their sudden reappearance is a crucial clue. In a frozen world, the global ocean is sealed under ice, cutting off the atmosphere. Without oxygen mixing in from the air, the seawater becomes starved of oxygen, allowing dissolved iron from volcanic vents on the seafloor to accumulate. When the ice finally melted, this iron would have rusted out in a great chemical pulse, falling to the bottom as those telltale red bands. So what could possibly trigger such a planet-wide disaster? The culprit appears to be life itself and the very gas we breathe. Remember the rise of cyanobacteria and their oxygen pollution. That great oxidation event over 2 billion years ago was likely the first climate shock. By breaking apart the methane greenhouse, it may have caused an earlier, less severe glaciation. But the later, more extreme snowball events required another trigger. One leading theory points to the breakup of a supercontinent. As the landmass fractured, vast new coastlines were exposed to rain and weathering. This supercharged the planet's natural thermostat, the carbon silicate cycle. Rainwater absorbed carbon dioxide and weathered the fresh rock at an enormous rate, pulling down greenhouse gases from the atmosphere faster than volcanoes could replace them. The planet's blanket thinned, temperatures dropped, and ice began to spread. Here, a runaway feedback took hold. Ice is brilliantly white, reflecting sunlight. As more ice formed, the planet's albedo increased, bouncing more of the sun's warmth back into space, which caused more cooling and more ice growth. This ice albedo feedback is a vicious circle, and once it passed a critical threshold, it could have plunged the entire world into the deep freeze within just a few thousand years. Earth's solution to the faint young sun paradox, it seems, contained the seeds of its own destruction. The very geological thermostat that provided stability could, under the right conditions, be cranked too far in one direction. For millions of years, the planet lay in its icy tomb, but the story does not end there because the thermostat was still ticking, slowly, deep beneath the ice. Volcanoes continued to erupt, with the continents locked under ice. Chemical weathering essentially stopped. There was no rain, no runoff, no mechanism to draw carbon dioxide out of the air. So with every eruption, the invisible greenhouse gas built up and built up with nowhere to go. Over millions of years, carbon dioxide levels climbed to heights almost unimaginable, perhaps hundreds of times higher than today's already elevated levels. This created a greenhouse effect of such staggering power that it finally began to overwhelm the brilliant reflectivity of the global ice. The thaw, when it came, was likely geologically rapid and spectacular. As the equatorial ice began to melt, dark ocean water was exposed, absorbing sunlight and accelerating the warming. The ice albedo feedback ran in reverse, and the global ice pack likely collapsed in a span of just a few centuries. The planet would have swung from a deep freeze into a scorching greenhouse, with torrential rains weathering the continents in a chemical frenzy, finally drawing down the catastrophic levels of carbon dioxide and restoring a new, fragile balance. These Snowball Earth episodes are not a contradiction of the faint young sun paradox, they are its dramatic sequel. They prove that the mechanisms which kept the early Earth warm were a dynamic and sometimes unstable partnership. Our planet's climate is not a steady state, but a story of precarious balances, violent overcorrections, and long, patient recoveries, written in ice and fire across billions of years. The faint young sun paradox is not just our story, it is a galactic condition. Every star like ours begins its life dimmer and cooler, which means every rocky planet orbiting within what we call the habitable zone faces the same brutal challenge of a frozen infancy. This realization completely transforms our search for alien life. That comfortable band around a star where liquid water can exist, the so-called Goldilocks zone, is not a fixed ring. It is a moving target, slowly migrating outward as the star ages and brightens. A planet that is perfectly temperate today under a mature sun like our own would have been an ice ball for its first few billion years. So when we scan the heavens and point our telescopes at a promising world orbiting in the current habitable zone of a sun-like star, we must ask a deeper question. Is it in the habitable zone now, or was it ever habitable long enough for life to arise and flourish? The paradox suggests that many potentially life-bearing worlds may have spent their youth in a deep freeze, a delay that could have stalled biological evolution before it even began. For life to have a chance, a planet needs more than just the right distance from its star. It needs a way to cheat the early freeze, just as Earth did. This means our checklist for a living world grows longer and more specific. We should be searching not just for planets in the right place, but for planets showing signs of powerful planetary warming systems. The chemical signature of a thick greenhouse atmosphere with high levels of carbon dioxide or even methane in the spectrum of an exoplanet's light would be a thrilling clue. Evidence of active volcanism or tectonic activity, though harder to detect from light years away, would hint at a working geological thermostat like our carbon silicate cycle. A world with a large moon might experience tidal heating, providing an internal furnace. We might even prioritize searching around stars that are slightly more massive and shorter-lived than our Sun, stars that spent less time in their dangerously faint youth, offering their planets a warmer head start. The faint young sun paradox, therefore, lifts our gaze from Earth's past to the cosmic future. It teaches us that habitability is not a snapshot but a saga. A planet must maintain its warmth consistently across billions of years, navigating the perilous early chapters of its star's life. This turns the paradox from a curious chapter in Earth's history into a universal principle, a new filter through which we view the galaxy. The silent, frozen worlds may outnumber the living ones, making our own blue marble not just a home, but a testament to an extraordinary and enduring cosmic balancing act. The latest models may point to a layered solution, but the ground beneath them is always shifting. Science rarely offers a final, tidy answer, and the faint young sun paradox is no exception. Just when a consensus seems to form, a new discovery emerges from the ancient rock record, challenging our assumptions and reigniting the entire debate. Some of the most recent geochemical analyses are doing exactly that, casting fresh doubt on the super greenhouse theory. By applying more precise techniques to those same ancient paleosols and marine sediments, a number of research teams have arrived at a startling conclusion. Their data suggests that carbon dioxide levels in the Archean atmosphere, while higher than today, may have been far lower than previously estimated, perhaps only 10 to 20 times modern levels, not the hundredfold increase once thought necessary. If these new numbers hold, the paradox slams back into focus with renewed force. A moderately enriched CO2 atmosphere, even amplified by pressure broadening, might simply not be enough to keep the global ocean liquid under a 70% sun. The primary suspect in our warming mystery suddenly has a much weaker alibi. This forces scientists to reconsider the entire atmospheric recipe. Could another ingredient have carried the warming load? One intriguing new alternative proposes a sky not of methane smog but of an ethane haze. Ethane is a heavier hydrocarbon, a molecule built from two carbon atoms. In the oxygen-free, methane-rich air of the early Earth, sunlight could have broken apart methane molecules that then recombined into these more complex chains. An ethane haze would have some unique advantages. It is less reflective than a methane smog, absorbing more sunlight directly to warm the upper atmosphere. It is also more chemically stable, meaning it would not break down as quickly, providing a longer-lasting blanket. This shifts the atmospheric chemistry in subtle but important ways, offering a different path to a warm planet without requiring impossibly high carbon dioxide. Yet, like all new ideas, it brings its own set of complex questions and awaits the hard test of geological evidence. Other researchers are digging into the very atoms of the air itself through the subtle language of isotopes. The ratio of different nitrogen isotopes preserved in ancient rocks can act as a barometer for the total pressure of the ancient atmosphere. Some of these studies suggest the early air might not have been dramatically denser after all, challenging the pressure broadening hypothesis. If the nitrogen blanket was not exceptionally thick, then the greenhouse gases within it would not have been as supercharged as the models require. Each new finding like this is a piece of a billion-year-old puzzle, and sometimes the pieces seem to belong to different pictures entirely. This is not a sign of failure, but the vibrant, messy process of science at work. The faint young sun paradox is not a closed case in a history book, it is a living mystery. Every improved instrument, every sharper model, and every newly analyzed grain of zircon from the dawn of time has the power to refine or even rewrite the story. We are not just learning about the past, we are witnessing the present tense of discovery, where each answer carefully unravels to reveal a deeper, more fascinating question beneath. Our planet's warmth has never been a single, static state, but a grand and evolving symphony, each geological era conducting the climate with a different set of instruments. To truly grasp how Earth cheated the freeze, we must walk through deep time, watching the solutions shift and adapt as the world itself transformed. The story begins in the violent Hadean Eon over 4 billion years ago. Here, under a sun shining with only 70% of today's light, the first warmth was likely brutal and temporary. A primordial hydrogen atmosphere, a puffy shroud captured from the solar nebula, may have provided an initial insulating halo. But the real heat came from the sky itself, in the form of cataclysmic impacts during the late heavy bombardment. Each colossal strike was a trauma that vaporized rock and ocean, injecting immense pulses of greenhouse gases into the air. The climate would have lurched between fiery, impact-driven saunas and chilling winters, a chaotic and unstable warmth that nevertheless kept the global ocean from locking into permanent ice. This was survival by repeated shock treatment, a world staying liquid through sheer violence. As the bombardment faded, Earth entered the Archean Eon, and a more sustained strategy took over. The faint sun still shone, but now the planet's own internal engines roared to life. With a thinner crust and furious tectonic activity, volcanoes pumped carbon dioxide into the atmosphere at a staggering rate, likely supplemented by methane from the earliest microbial life. This created that thick, super greenhouse blanket, amplified by a denser nitrogen sky. Crucially, the planet was still a water world, its dark, global ocean absorbing every photon of weak sunlight and distributing the heat through unimpeded currents. The carbon silicate cycle, that geological thermostat, was now active but set to a much higher temperature, constantly replenishing the CO2 that the faint sun's weakness demanded. For well over 1 billion years, this powerful combination, a hyperactive geology, a potent atmosphere, and a dark, fluid surface maintained a stable, if alien, warmth that allowed life to establish its first fragile footholds. This long stability was shattered in the Proterozoic Eon. Life itself, in the form of oxygen-producing cyanobacteria, began to dismantle the very greenhouse that nurtured it. The Great Oxidation Event scrubbed methane from the air and likely triggered the planet's first global glaciations. The carbon silicate cycle, once a source of stability, now became an agent of chaos. The breakup of supercontinents exposed fresh rock to weathering, which pulled down carbon dioxide so efficiently that it overpowered volcanic inputs. This plunged Earth into the profound snowball events where ice reached the equator. These were the paradox dark twins, periods where the balancing act failed completely. Yet even here, the planet's enduring mechanisms provided salvation. Volcanoes continued erupting under the ice, building up carbon dioxide over millions of years until the greenhouse effect grew so monstrous it melted the global ice in a geological instant. The Proterozoic was a time of wild pendulum swings, proving that the solutions to the faint young sun paradox were dynamic and could be violently overturned. Finally, we arrive at the Phanerozoic Eon, the last 540 million years, the age of visible life. By this chapter, the sun had brightened significantly, approaching its modern strength. The desperate, extreme measures of the earlier eons were no longer necessary. The carbon silicate cycle could operate with more subtlety, maintaining carbon dioxide at lower, more moderate levels. Continents had assembled and drifted, shaping ocean currents and creating diverse climates, from tropical reefs to polar ice caps. Life's influence on the atmosphere became dominant, with plants and algae actively participating in the carbon cycle. The faint young sun paradox was, in essence, over. The star had finally grown into a reliable source of warmth, and Earth systems could settle into a finer, if still occasionally unstable, balance. The frantic struggle against the freeze had given way to the complex, vibrant dance of climates we recognize today. This long timeline reveals the true nature of our planet's habitability. It is not a gift but a legacy, hard-won across billions of years of relentless geological and biological innovation. So the grand experiment of our solar system produced 3 rocky worlds, but only one enduring home. Venus, Earth, and Mars each faced the same faint young sun, yet their climates diverged onto paths of fire, balance, and ice. This stark comparison reveals the true nature of Earth's success. It was not one single miracle, but a perfect and precarious alignment of cosmic good fortune. Our planet's size was the first critical piece of luck. It was large enough to retain a substantial atmosphere against the solar wind's erosive force, yet not so massive that its gravity would crush us under a crushing blanket of gas. This Goldilocks gravity also provided the internal heat needed to drive plate tectonics, that relentless geological engine which recycles carbon and regulates temperature over eons. Mars, smaller and cooler inside, saw its tectonic activity stall. Its atmosphere leaked away into space, and without that recycling mechanism, its greenhouse collapsed into permanent winter. Earth's distance from the Sun was the second vital factor, placing it squarely in a zone where liquid water was possible. But as we have seen, distance alone was insufficient under a faint star. This is where the third ingredient came in, our planet's profound geological hyperactivity in its youth. A faster spinning, hotter interior fueled rampant volcanism, ensuring the carbon dioxide needed for a thick greenhouse blanket it was constantly replenished, fighting the cold at a rate the weathering cycle could not immediately counteract. Then there was the water world itself, a global ocean of stunning dark blue that soaked up every precious photon of weak sunlight, its vast thermal mass smoothing out climatic shocks and its unobstructed currents distributing warmth from pole to pole. Contrast this with Venus, which may have started with similar oceans. Being closer to the Sun, it received more of that early warmth, but this proved its ultimate downfall. A little extra heat likely triggered a runaway greenhouse effect, boiling its oceans away and leaving behind a dead world shrouded in a suffocating carbon dioxide atmosphere with no water left to drive a weathering cycle. Venus solved the paradox too well, and its thermostat broke forever. Earth's recipe, therefore, was a specific and sequential blend. Take a planet of just the right mass and composition. Place it at just the right orbital distance, add a massive early ocean and a frenetic geological heartbeat, stir in a primordial atmosphere thick with heat-trapping gases, possibly amplified by the biological whispers of the first microbes. Allow it to simmer for 1 billion years under a dim star, its systems constantly interacting and adjusting. The faint young sun paradox was not solved by a single clever trick, but by a planetary symphony where every instrument had to play its part in harmony. Remove one element, a smaller size, a slower geology, a different atmospheric mix, and the music falls apart into silence or cacophony. This realization transforms the paradox from a fascinating puzzle of Earth's past into a profound insight about our place in the cosmos. It suggests that persistent, stable habitability across billions of years is not a common default setting for rocky worlds. It is a delicate, hard-won state, a fleeting equilibrium maintained by a rare confluence of circumstances. Our existence here is the product of that perfect storm, a legacy written in the long defiance of the cold. That delicate balance of fire and ice will not last forever. Our planet's long-term forecast, written in the laws of physics and stellar evolution, is one of escalating heat. The same sun that was once too faint now holds our future in its slowly brightening glow. Over the next billion years, our star will continue its inevitable march toward greater luminosity, growing roughly 10% brighter every billion years. This gradual increase will fundamentally break the carbon silicate cycle, the very geological thermostat that saved us from the ancient freeze. For eons, this cycle has been our climate guardian. Increased warmth leads to more rainfall and faster weathering of rocks, which pulls carbon dioxide from the air, cooling the planet in a beautiful negative feedback loop. But there is a limit to its power. As the sun's output climbs, the cycle will begin to work against us. Higher temperatures will supercharge the weathering process, scrubbing carbon dioxide from the atmosphere at an ever-accelerating rate. Volcanoes will keep adding new carbon dioxide, but they cannot keep pace with the frenzied chemical erosion driven by a hotter, wetter world. The planet's primary greenhouse gas will be drawn down to critically low levels. This might sound like a good thing, a planetary air conditioner kicking into overdrive, but it is a trap. With less carbon dioxide in the air to trap heat, the planet will rely more and more on the sheer intensity of the sunlight itself to stay warm. The thermostat will be turned down just as the furnace is being cranked up. For a while, these opposing forces will struggle, but the sun is relentless. Within about 600 million years, the increased solar energy will be so great that the carbon silicate cycle will fail completely. The concentration of carbon dioxide will fall so low that most plants, which rely on it for photosynthesis, will begin to die off. The greening of our world will reverse. The skies will clear of their greenhouse blanket just as the sunshine becomes unbearably fierce. This is the prelude to the end. Around 1 billion years from now, the sun will be about 10% brighter than today. That extra energy will cross a critical threshold. The increased heat will cause massive evaporation from the oceans, pumping the atmosphere full of water vapor, which is itself a potent greenhouse gas. More water vapor means more warming, which means more evaporation in a vicious, self-reinforcing cycle. This is the runaway greenhouse effect. The planet's temperature will begin to soar uncontrollably. The oceans will not simply evaporate, they will boil. Global temperatures will climb to hundreds of degrees, hot enough to melt lead. The last of the liquid water will be driven into the upper atmosphere, where intense ultraviolet sunlight will split the molecules apart, allowing the lightweight hydrogen to escape into space forever. Our blue marble, the water world that defied the ice for so long, will be left a barren, scorched rock under a hazy, carbon dioxide-rich sky. It will become a second Venus. This future mirrors the paradox of our past with a cruel symmetry. For billions of years, our planet ingeniously fought off the deep freeze imposed by a faint young sun. It used every geological and biological trick to trap and retain every scrap of warmth. In the distant future, those same systems will be overpowered from the opposite direction. The struggle against the cold will be replaced by an inescapable march into the fire. Our story, it seems, is bookended by stellar extremes, a long, vibrant summer nestled between an age of potential ice and an era of certain flame. This cosmic perspective frames our current moment with profound poignancy. We exist in the precious, stable middle chapter, the product of a billion-year defiance of winter, and a billion years away from the inevitable summer that will consume us. The faint young sun paradox is not a single riddle, but a grand tapestry woven from many threads. Our planet's early warmth was not the work of a lone hero, but a planetary alliance. A hyperactive geology pumped immense amounts of carbon dioxide into the skies, building a supercharged greenhouse blanket. That blanket may have been amplified by a thicker, heavier atmosphere, where pressure turned every greenhouse molecule into a more efficient heat trap. Unique conditions, from a darker global ocean to a potentially faster spin, tilted the scales against the ice, and underpinning it all was the relentless, stabilizing heartbeat of Earth's geological cycles, the carbon silicate thermostat that provided feedback and control over millions of years. This mystery underscores a profound truth. Our planet's climate is not a static setting, but a dynamic, finely tuned, and astonishingly resilient system. It is a system that can be pushed to the brink of global ice or scorching heat, yet finds ways to correct, to adapt, and to endure. The most powerful takeaway from this entire cosmic detective story is elegantly simple. The fact that we are here today, able to ponder this ancient puzzle, is the ultimate proof. It is living evidence that our world, against formidable odds, found a way to stay warm. It navigated the long winter of its star's youth, preserving the liquid water and stable conditions that allowed life to spark, evolve, and eventually look back at the stars with wonder. Which piece of this ancient solution do you find the most fascinating? Was it the planetary thermostat, the strange chemistry of a methane haze, or the brute force of a sky under pressure? Let us know your thoughts in the comments below, and if you enjoyed this deep dive into one of Earth's oldest mysteries, be sure to subscribe. We are just getting started exploring the incredible stories written in the rocks and the stars.